Hello everyone, welcome to this talk today where we're going to be looking at connection design, specifically bolted and welded connections, but the principles we look at here can be used in a wide variety of ways, although we're only going to cover sort of the basic details of connection design. Now, just an overview, we're going to go through some typical connections, then design of bolts, design of simple connections, and then bolted connection with eccentric loads, welds in connections, and design for eccentric loading on welds. And the Green Book is no longer a compulsory book for this course, although it's a really good resource. So this is the South African Institute of Steel Construction Green Book on Connections. Much of this lecture is taken from that, but I really encourage you to go get hold of a copy of that for the future. It's an excellent resource for structural engineers. If you have a look at the structure shown on the right-hand side here, this is a multi-story industrial structure. In a building like this, there will be a lot of connections because ultimately you bring a whole bunch of steel pieces to site and then they are erected on site and put together in its final form. So what will happen in a workshop somewhere, various smaller pieces will be welded together, so you'll then create assemblies. So an assembly is, for instance, a column with cleats and base plates and various things welded onto it. You will then send the completed welded assembly to site, and then on site you erect the assembly and you bolt it together. Because what happens is you typically shop weld, site bolt. You don't really want a welder around all over the show on site. The quality can be a problem, so ideally everything on site should be bolted together, although in reality that often does not happen, but that's what we strive to get towards. Now, here's some various typical connections, and this is the steel connection tree at Stellenbosch, kindly donated by industry. And you've got a typical haunched connection at 1, so deep connection, bolts far apart as possible to create a moment and transfer moment from the beam to the column, and then stiffener here where you have some bearing force against the column. Then you've got an end plate of a circular hollow section, so that's just a very simple end plate welded onto the pipe, and then purlin connected using an angle at 3, so an angle welded on, or bolted onto a beam or a rafter, another one here, and then you just bolt onto the cold form lip channels. Then you've got a circular hollow section bracing, and you'll see here a steel plate was actually cut into the circular hollow section. So a slot was cut in the pipe and then a plate inserted, and then it was welded up so it could be connected on. And then we've got a web stiffener at 5, as I was discussing earlier, extended end plate at 6. So here, to get a bit of moment capacity, the end plate was extended, and then we have a bigger lever arm for the bolts through it. And then we've got just a simple angle cleat. This is a very common type of connection, pinned connection, and it makes fabrication and erection quite easy because there's a bit of tolerance and a relatively cheaper connection to make, so you don't have to weld anything in the shop, but it transmits no moment, whereas the number 6 does transmit moment. And you can foresee a steel structure as a giant Meccano set, and you need to decide how are you going to connect this thing together in an efficient way, because at the end of the day, connections can account for a lot of money. The cost of the workshop and the welding and the different details and bolts, etc., can add up a lot. And good connection details, simple connection details, can bring down the cost of a steel structure a lot and make it a lot more efficient. And also, using standardized connections, you can result in fewer mistakes and fewer problems, and generally a more reliable structure. So consider connections very carefully. Here's some other examples. For instance, there's once again another pipe bolted onto a column, a end plate on a beam, a little knee brace stabilizing a rafter, and then purlin connected to a beam there, and then some bracing coming into the corner here, so that's some bracing, and then some deeper and quite large connections on the right hand side. So these are quite heavy beams, and the right hand one's a plate girder bolted onto a column. So this is all from a Tekla model. So when it comes to bolts and bolt connections, we firstly need to know what is the grade of the bolt. And you've got three main grades: 4.8, 8.8, 10.9. The most common for structural use is 8.8. So if in doubt, it probably at 8.8. However, in reality, in many situations, 4.8 is probably sufficient. Um, and in some of the older engineers would, actually used to use 4.8s quite commonly, but now with 8.8s being so easily available, they often specify it throughout, except for perhaps the purlins and the cold form sections, which have the grade 4.8. Now, in the grade, the numbers have an important representation. X, the first number, so the 4 for instance, is the nominal strength multiplied by 100 to get MPa, and then Y is the yield or proof strength as a proportion. So 4.8, 400 MPa times 0.8 is 320. However, we normally use the ultimate strength for design. So we're going to be focusing primarily on this section here, the yellow section. So it's either going to be a 420 or 800 or 830, depending on the diameter, and 1040 for grade 8.9. I'll be perfectly honest, this is where I often make a mistake. You're not paying attention, and then depending on the bolt diameter, you need to use a slightly different yield strength. If in doubt, go with the lower one, and then you're safe. But the proper calculation should have the 830 if you have a bolt size greater than 16 mils. And then you have very standard bolt sizes that you use. So they're only specific increments that you can use. Now, in a separate video, this table here is discussed, going through all the different capacities and how we get to them. So you can refer to that video, which will assist you with it. One thing you may not be able to see on the screen, depending on the resolution, is on the edge of each bolt, it's actually written what grade it is. And this one here says 8.8. So this is a high tensile bolt that we are looking at down there. Now, once again, these are covered in a separate video that you can refer to. When it comes to bolt resistance, we need to make sure that we know whether it's in single shear or double shear. And bolts are commonly in shear when loaded, but single or double refers to how many planes will fail when it's pulled. For instance, these two bolts that I'm highlighting have one failure plane, whereas a double shear, for this middle plate to pull out, each bolt has to fail along two planes. And so what you'll see is to go from here to there, you simply multiply by 2. Double shear has double the capacity because it's double the area of failure plane that you need. So just be careful when calculating capacity. Is it single shear or double shear you're looking at? And you need to know a little bit about the connection to be able to do that. Now, on the right-hand side, this I've just taken from the Steel Construction Handbook. Also, this is from the Green Book, and it's the same as the Red Book, the South African Steel Construction Handbook guidelines, and a lot of details have been pre-calculated here, such as the capacity of bolts, the bearing resistance per millimeter of plate thickness, so that you simply multiplied a value there by a thickness, and you'll get to a bearing resistance. And then where other ones are VR, and this is TR. So you can use these tables for checking results. In our course, you can only use those resources if you are told. Otherwise, you do need to calculate them from scratch. Now, also here we have a bolt group, because if you have a bolt in single shear and it's in pure shear, it's very easy to calculate the resistance. We would simply take the resistance. Let's say we've got an M24 bolt, it's grade 8.8, it's in single shear. We just take the capacity and multiply by the number of bolts, and it's done. We'd also check the bearing resistance, etc., but it is a very simple check. It's just the lowest of either the bearing resistance or the shear resistance. But when it comes to a bolt group, we need to have a look at how stressed all the bolts are, but more importantly, which is the most stressed out of all of it. For instance, here's a bolt group loaded in plane, so there's a force here, and all 12 bolts get stressed, and we, for instance, find that this bolt here is the most stressed. You will see a separate video to this one where we cover the derivation of the equation for calculating the capacity, but so we're going to not include that here, but I'm just going to discuss the basics of bolt design of a bolt group. For instance, we're looking at bolt J there. When it comes to bolt J, we would need to firstly check what is the shear resistance, bearing resistance, and then you can also have bearing resistance with edge pull out. I'll just call it A because there was that edge. Distance, and now what you have there is that we choose the minimum of those, and of these shear or bearing resistance, what we will find is then one of those governs, and then the most stressed bolt in the entire group. So we've got 12 bolts. We need to make sure that the most stressed bolt at its weakest is strong enough. So we'd calculate the forces, find out, for instance, bolt J is the most stressed, and then we would need to make sure that bolt J is strong enough. So let's say it's 80 or 90% stressed, then we know that definitely all the other bolts will be more than sufficient. So that's the way of going about a bolt group in plane. And by in plane, just in case it's not clear, that means is, for instance, if I look at my elevation of the other one, I've got forces on it. Those forces are causing a shear failure in these bolts. So as the connection tries to move, it tries to shear through those bolts. So we are checking the bolt group failing in plane. Firstly, when you consider a bolt group, one of the important things to know is where is your center of bolt group rotation, which is in the middle of the group. If it's a symmetric or a doubly symmetric section, it's very easy. It's always just straight slap bang in the middle there, and we can find that just by inspection. But if you have it's not perfectly symmetric, you can calculate it where the center of rotation from some arbitrary position. So, for instance, you start from the bottom left side and you calculate it from there, you will then end up finding an XC value and a YC value from there. Once you have the center of rotation, you work out everything from there. So once you've got your center of rotation, you forget the distance to the arbitrary point, you forget about the arbitrary point that you started with. You just work from the center of rotation and the center of rotation to the bolts. Now, with the derivation here, what you will normally find is that the bolt size is all the same. So we just, you don't actually need the area of each bolt. You simply need the sum of the Y distances or the X distances divided by the number of bolts. One thing to note, though, that with this and the equation on the next page, this is a simplified approach. There are updated potentially more accurate methods available. We're going through a simple method to calculate it, so just be aware there are various other methods out there more advanced than what we're doing. So there's some approximations in what we are doing. So as I was saying, when you are calculating the force in one bolt, here is the equation you use to define it. And as I said, this is derived in a separate video. So you run through and then you pick out which bolt is the most stressed. And you can work that out by a vector sum, which is shown in the worked example and the other derivation videos. And once you've identified the most stressed bolt, that you calculate the force at it. And as I was mentioning, you check this against your minimum of your shear resistance and your bearing resistances. So we've got to make sure that the force in a bolt, so FUJ is the force in one bolt, not all 12 bolts. Do not multiply the capacity by 12 or 3 or however many bolts there are. It is purely for one bolt. And so the capacity would be 86 or 34 or 92 or whatever kilonewton value it is. Now, when it comes to the bolts, the number of bolts in their distribution is accounted for in the equation by N and the polar moment of inertia. So the polar moment of inertia is just the X and y values squared, x squared plus y squared, accounting for the distance from the center of rotation. From the center of rotation. It's very easy to make that mistake. I've done it a few times when you take it from some other point, but always just pay attention. You work out the center of rotation and you use it and measure everything from it. And we will do an example to illustrate this. And then just a quick note, if you are using the red book, you just need to make a correction to the one equation if you are using this from this. As I said, x, I, and y are taken relative to the center of rotation, and see online for the derivation of this, and then also the application of this in a worked example. Now, moving on to welds. Welds commonly used, as we said, in shops for welding different sections together. If matching electrodes are used for welds, the weld strength will be higher than the parent material. Hence, we just use the strength of the steel section. So, for instance, electrodes starting with D7, E7, F7 are suitable even for S355JR. And this number in front, for instance, E70XX, the number, that 70 is a value in KSI, kips per square inch, and you convert it and you end up with a value of 482. So we generally use the value of rounded off to 480. So when we're using S355 steel, a weld strength, the ultimate weld strength we normally work with is 480 MPa. So this will be our design strength XU. And just be careful, there is a difference between F subscript U, which is the steel, and then X, which is the weld. Now, there are different types of welds we can use in a structure. Typically, these are shown here. For instance, you've got complete or partial joint penetration groove welds, and complete is when there is full penetration, so the full section is effective, where partial is only part of it is effective. So when you're considering the capacity of those, base metal or weld metal could govern, depending on this. Once again, we said that in most cases, if the failure type is the same, for instance, it's tension failure for both, and then the steel is slightly weaker than the weld, so we would only really check the base metal in many cases if we know that the weld metal is stronger. But there are cases, especially with fillet welds, where you'll see that's not the case. So you can see very quickly from the slide how to work out the areas for the different ones. But we're just trying to see when it fails, where will it fail. So it's either the full section, we use the full section, or we use partial section for it. So yeah, so there's complete and there's a partial penetration. For a complete joint penetration groove weld, the AM does not need to be calculated, so instead we simply take the resistance to be the following. And so we can also take it as such. So that simplifies our life a lot. We have a much simpler equation to work with there when we are designing it to get our resistance. Now, the tensile resistance is also given here. So this is a simple equation. For instance, here, and if we have a weld all the way through, that would be working out the tension force TU, and then we'd have it some sort of, if it's a full weld, a TR resistance of that, which we would make sure there's less than the capacity of the steel. We can also have cases where we've got to check a weld, well, check a portion of a weld. For instance, if we wanted to check that of a fillet weld, that would be the tension resistance. But since shear is weaker, we normally ignore it. There may be sort of exceptions when we require to test it, but this is the tension resistance of a weld, so where that's in pure tension. So, as I mentioned previously, fillet welds are the most common types of weld, and these normally are what we would design for. The bulk of welds in any structure are actually fillet welds. So invariably, this is what we will be designing. And they're quite easy because you can simply take a piece of steel and another piece of steel, butt them up against each other and weld it up. And so we will then design it for a specific shape, but we're going to assume that this is just a pure triangle. We ignore that bulge and then the rounded section, and so we use a width, a TW. And just be careful, there is a difference between a TW and a W. A TW is the diagonal, a W is the total width. So we would normally use this for the specified width. For instance, you refer to a 5 mm weld. A 5 mm refers to that horizontal distance, whereas the narrowest distance, a TW, may be what fails. Just two things to note is that the orientation of the force affects the capacity. The resistance of a fillet weld depends on the direction in which it is loaded, longitudinal, at right angles, or in between. So be careful of that. And then weld groups can be subjected to combined stresses in the same way that bolt groups are, and we'll have a bit of a derivation of that. And if in doubt, just assume that the layout A is what we're using, and that is the sort of general fillet weld that will be specified. So unless told otherwise, that's what you can use. You'd have to adjust your equations for any of the other welds shown here. So, for instance, here is a weld, or a fillet weld on a section enlarged, and what you end up with is, for instance, you may have a weld upwards, FUP, a weld horizontally, FU, a shear weld, but then you can also then have a resultant. We want to make sure that the weld can carry that resultant. And so we need to make sure that where the forces are acting, it is sufficient. The most stressed 1 mm of weld is sufficient for that. So, and just as a separate note, for the shear force and tension force in a weld, as I was mentioning, we've got a tension force there, we've got a shear force on the side. Shear is weaker than tension, so we always design the fillet welds as if in shear. Makes our lives easier, we only have to check one. Both are happening, but since shear is less, we only then check the shear. So, yeah, so there's the different sides. So let's start applying this and then finding out how do we calculate the capacity of these welds. Now, what's important is that the resistance, and this is then now for a most stressed 1 mm of weld, the resistance of a fillet weld with load applied an angle of theta to the longitudinal. So there's 1 mm of weld somewhere that we're designing, and it is an angle theta, so to the horizontal, and we need to make sure it satisfies this equation. So you'll see theta appearing in there, and also a TW. Remember, just be careful, a TW sine of 45 times AW, the easiest way is just to use that, 0.707 AW. So just be very careful. Remember, AW would be, e.g., a 5 mm weld, and then you would multiply by 5 by 0.707, and then we need to make sure that this is less than or equal to the material. So the first part is the weld, the second part is the material. Either could govern. Either could govern. So just be careful of that. At different angles of theta, different capacities govern, and you need to check both and make sure which one governs. If you have combined stresses, for instance, if you've got a stresses in multiple directions, a three-dimensional, you can include it in this way as shown here, and calculate your angle as listed there. A bit more complicated, but it can be done if you have shear in both directions and a moment acting on a connection. So yeah. So now, for instance, in a general connection, you may have a weld, and then it's a length LW, a force, a shear force, and a moment are applied to it. This is going to cause a stress state in it, and we need to make sure the most stressed 1 mm wherever that side is. It's normally on the edge, either that side there or that side there. We need to make sure that millimeter is sufficient. But for instance, if we have a longer weld, now let's look at B. It's just a weld once again, but let's say now it has a single force P applied to it. And this acts at a distance or an eccentricity E and at an angle. What we will first need to do is convert that into a perpendicular and shear force, and then once we have those two forces, move them to the middle by converting the force at a distance to a moment. So we convert that force PU into three different items: a shear force, a perpendicular force, and a moment, and then we will design for it. Always when designing with welds, take everything to the middle of the weld and then start from there. Irrespective of where the forces are, just get the forces acting at the middle. Get forces at middle of weld, always. And it'll make your life a lot simpler when it comes to the design. So now, for A, the forces act, sorry, I've drawn over the text. For A, the forces act at the centroid of the weld, so weld forces can easily be solved for. And then for B, the force of PU is applied at eccentricity. And then I've just explained how you would transfer that to the middle. But now let's have a look at what those stresses will look like. For a weld subjected to an eccentric force, the loading should be converted to a moment, axial force, and shear force acting at the centroid of the weld. So, for instance, if you want to calculate now these stresses, the perpendicular force or stress, you have firstly a vertical force, F, divided by LW. So what this would look like is you have a force and you distribute it over the length of the weld. So if this is a weld of LW, it has an upward force here of FU. This would be just distributed as FU divided by LW. That would give you an average stress along it. But then now what you have is also a moment. So for instance, we take this, we have a moment. The moment causes a stress distribution identical to that which you see in a beam. Plane sections remain plane, linear stress distribution. So here you end up with the stress profile ranging from one side to another. And at the extreme here, that value is 6 mu over LW squared. And that is just the same as having a ZE of LW squared over 6, and where your moment is Z times Fy. I'm just taking you back to bending theory for beams, and that is where this would come forth, because you've got a 1 millimeter wide weld, or a unit width of times L squared over 6, so that's an elastic modulus. An elastic modulus gives you the stress in an elastic distribution, and so we can convert then, well, we mix this equation round, and we can then find the stress, which is 6 mu over LW squared. Be very careful with LW. If you have a weld on both sides, what you need to do is you have 2 LW, where the LW squared and the 2 is on the outside. If you take 2 LW and then square the whole thing, you've got a problem, because what you are saying is it's actually a double the length weld, not 2 welds next to each other. So this is 2 welds next to each other. That is the physical length. So just be careful when you're doing calculations. If you have a weld on both sides, it's 2 times separate LW squared. Now, so let's move on to the next part. Here we have a shear force of VU, and then this would cause a stress along the length like that. And that then gives you the different components of stress or force. So you've got then your perpendicular, you've got your longitudinal, you get your resultant as you've seen earlier, and then you also calculate the angle of the resultant. And so, for instance, what you would find in this case is that you end up with a resultant here, f, small f, at some angle theta. Theta and f subscript u have nothing to do with the angle of the applied force. Convert everything to the center of rotation, find the perpendicular stresses, find the shear stresses. Then you find a resultant or force, this f u, and then the angle of it relative to the axis. It has nothing to do with the angle of the applied forces and moments separately. So just that's a common mistake people make. Just be very careful of that. So yeah, so that gives you very quick overview of then just the stresses you look at when designing for a weld. And then last thing just to have a look at is the fillet weld capacity when you can simplify it. For instance, here you see a connection with two forces applied, and to get into a weld group calculation with perpendicular forces and moments, etc., can become quite complicated. So you can make your life easier just by converting this into a virtual gusset, where you just trace a straight section and then use that so you have no moment. So you only design a reduced width, so either that width there or that width there, and then you can design that for with no moment in mind, and you've just ignored all the material on the outside. So it's a quick way of checking your design. So yeah, just that's a note on using virtual gussets. Okay, so that takes us through then the use of the general design of connections and welds, and hopefully that makes it a little bit easier for you to apply this work. Thanks.